In this lecture, we will be talking about the cardiac axis. The cardiac axis is the net direction of depolarization of the heart. So if you add up all those different vectors and depolarizations of the heart, what would be the combined direction that they are going in? So which one wins out? An abnormal axis, particularly one that is changed from a previous EKG, warrants further evaluation. Some conditions that can cause changes in cardiac axis include myocardial infarction, hypertrophy, and conduction delays. So let's look at some different hearts here. This first one is a normal heart and has a normal cardiac axis, which would be somewhere between negative 30 degrees and positive 90 degrees. So somewhere around here. This because the left ventricle is more massive than the right ventricle, so you'll have more depolarization going on in this area here, giving you an axis in this region. Now, let's take a heart that has left ventricular hypertrophy. If this is the normal axis, since now we have more tissue density on this side and thus greater depolarization, the axis will be shifted towards the region of hypertrophy. On the flip side, let's say we have a heart that has suffered a myocardial infarction in this region here. Since the tissue no longer depolarizes, you will have more depolarization comparatively going on the right side, and this would shift the cardiac axis towards the right ventricle. Next, let's learn how we can estimate the cardiac axis from an EKG strip. Here we have a normal heart with a normal cardiac axis somewhere in between 0 and 90 degrees. And here we have our EKG printout. The first lead that we're going to want to look at when we're trying to localize the cardiac axis is lead 1. If we recall, lead 1, it goes from the right arm to the left arm electrode and is here on our EKG printout. So any depolarization that is moving along lead 1 and towards our left arm electrode will be recorded as positive on the EKG strip. So in this case, since the net depolarization is moving in this direction alongside lead 1, we have a positive deflection of the QRS complex in that lead. The second lead we want to look at is AVF, which if we recall is perpendicular to lead 1 and is found here on our EKG printout. Similarly, since we have this net depolarization moving along our AVF lead towards our AVF electrode, we have again a positive QRS complex in that lead. So this narrows down our cardiac axis to this quadrant here between 0 and 90 degrees. Let's look at another example. Starting off, first lead we want to look at is lead 1. Is the QRS complex primarily positive or negative? In this case, it's primarily negative. This tells us that the cardiac axis is somewhere on this half of the heart. To narrow it down further, we look at lead AVF. Is it positive or negative in terms of the QRS complex? Here it's positive. That means our cardiac axis lies on this bottom half of the heart. So combined, our axis is narrowed down to this quadrant here. So for this particular heart and EKG, we have some right axis deviation. Since the axis is deviated from its normal of between 0 and 90 to somewhere between 90 and 180. For those of you interested, we can take this one step further and specify the cardiac axis even more. So let's stick with our same example and quickly recall what happens if we have an electrode and depolarization moving along it like so. In that case, we would get an isoelectric wave on the EKG. So let's see which one of these 6 leads gives us the most isoelectric QRS complex. In this case, it's lead AVR. So let's draw it into our heart here. and lead AVR would give us an angle of negative 150 degrees. So since the net depolarization is isoelectric with AVR, that means its direction is going to be perpendicular to this lead. So we can take our negative 150 for the lead, add in 90 degrees, which would bring us to a cardiac axis of 120 degrees. So to sum up, whenever you're trying to estimate the cardiac axis, you will always start off by looking at leads 1 and AVF to narrow down the quadrant. And then, if you want to take it a step further, you can find the most isoelectric lead out of these 6, and you'll know that the cardiac axis is going to be perpendicular to it. And that is cardiac axis.